How's the assignment? Yep. I'm trying right now. What you have and what you do. Later, issue is tell us when we cycle. Sorry. Okay.
Okay, maybe we can start. Time is precious. So Maths department has this Math Health Center. If you have problem with assignment or anything, you can go and meet the master or PhD students. So they will be around Tuesday, Wednesday, Thursday, 1 to 2 p.m. at A5G08 on this block. Okay, so you can meet the students, or if you want to meet me, you come to my office hour. So later, I will have an office hour from 10 to 12. So you can drop by if you're free. Okay, so I did a few updates. I think hopefully this is the final update. Tomorrow is the due date. So please download the latest version. And I changed some of the mark because I removed some of the question, but you still will get to do those questions, but those questions will be pushed to assignment 2. Okay. Yeah. Um, so let's clear up something first. So last time I talked about 2 cycle, right? Uh, 2 cycles look like this. IJ. Okay. It's called exposition. Um, so in the assignment, there's a word called 3 cycle, right? Last time. Did you see 3 cycle in the previous assignment? That. So what's a 3 cycle? What do you think? Yeah. So IJK. Okay. So in general, we can define n cycle. So maybe I1, I2, up to In. So how should we define this n cycle? How should we define n cycle? First of all, where's this element lies in? A cycle is an element where Sn. Okay. So first of all, n cycle is an element in Sn. But how does it look like? So you should think about what are the possible way to put n numbers together. Do we call for example, this one has a 4 cycle? No. Right, because we are thinking of this cycle as putting all the n indexes into a cycle. Again, we call it n cycle. Right. So what's the difference between these two? So now the structure coming already. So what's the fundamental difference between for example, let's say 1, 2, 3, 4. Okay. So this we will call a 4 cycle. This we don't want. So what's the fundamental difference here? What's the second one? 1, 2, and then 3, 4. Without what? Without transposition? Not enough. Product to what? What kind of transposition? Disjoint. Okay, so product of disjoint cycle. So meaning n cycle is an element in Sn that cannot be written as a product of disjoint cycle. Okay. Is this enough? Okay. Yeah. Any questions about n cycles? Okay. Next. Try. Yeah. So I want to talk about this notation here. So last time you were a bit confused with this set I wrote down. So let's say H is in group G, set of group G, and then we take some element, okay, for G, and then we take S to the power n. Okay. So I didn't introduce well about this notation here. So what do I mean by Sn here? So Sn meaning you compose S n times. I don't care what kind of composition here. Could be plus, could be multiply, could be function composition, okay, anything, okay. But the power will tell you how many times you will compose. Okay, how many times you compose. Is it okay? Better? Okay. And of course, you should ask what is 0? Do I put nothing here? What is 0? What does 0 supposed to be? Okay, so this is the question. So this is, I think this is only well defined for n greater or equal to 1. Okay, how about 0? 0 last time we verified that it has to be the identity in the group. It has to be the identity in the group. This is what we verified. Okay, because we check what happened if we compose S0 with the others. It satisfies the identity property. Okay. Okay. This is when we check that H is a subgroup of G. What do we call this subgroup? Anyone remember? What do we call this subgroup? Call it. Start with the C. What's this? The name of this group? Cyclic subgroup. Okay. So this is a cyclic subgroup. Okay. Why is this cyclic? You know what cycle like this? Okay. So you keep doing the same thing, compose the same thing. Okay. You have a cycle, cyclic. So you keep composing the same thing. Okay. So it's called cyclic subgroup. Okay. So you can see the cyclicity better when the order of n is finite. Remember what's the order of an element? What's an order of an element? What's an order of an element? Order is the number what? What does this order do? Order. So you know order, what is order? You mean like, for example, in the court, right? So the judge is a judge. Yeah, judge. The judge will say order. What does it mean? Huh? You know, like the judge will hit the hammer, right? And then order. What does it mean? Huh? Hello. 没有看过，不知道。不要玩这么多游戏啊，朋友。Okay. Yeah. Yeah. So the judge say order. So meaning everyone have to go back to normal. Okay. No more fighting, no more chit-chatting. Okay. Go back to order. Go back to normal. So here order. This X here need to return to where? No, not return to X. Not return yourself. Return to yourself. Return to identity. Okay. This N is for the X to return to identity. Okay. So this is the smallest positive integer such that s to the power n equals to identity. Okay, go back to identity. Remember last time I told you in group we put it inverse because we are somehow a way to go back to identity always. So n is the order is the smallest positive integer for x to return to identity. So do how many times you return to identity. So what's the very first example you see this? What's the very first example you see this kind of phenomenon? In the integer modulo n. Okay. So in integer modulo n, for example what? Let's take Z3, okay? Let's take Z3. What happens is Z3 plus 2 plus 2 equals to 0. Mod 3. Okay? So meaning the order of 2 is 3 in integer modulo 3. Okay? Why not 2 or 1? Because when you add 1 times, it's not 0 yet. Add twice, it's also not 0 yet. Okay, so this is the smallest positive integer such that 2 adding 3 times is the identity. Okay, so in this case here, we'll say the order of 2 is 3. Ready? Z3. Okay, is it okay? So you need to argue why is it the smallest one? Because less than it is not identity yet. Yeah, question. Can, but 1 can, yeah. So we also can ask about what is the order of 1. Okay, so what's the order of 1? Okay, so we do 1. Okay, so to be precise, we put a plus bar here. If you like, I put plus bar here. Everything I need to put bar. So sometimes, right, we don't put bar anymore. We understand we have a bar. You see, if I put a lot of bar, you'll see a lot of bar here. Okay, later you get your head around. So what's the order of 1? So, Shen, you suggest what? The order is? Order. Order is a number. So what's the order of 1? 3. Okay, so you suggest that the order of 1 is 3. So let's check it. Okay, so if I do once, okay, it's not 0 yet. It's not the identity in our group. I do twice, it's just 2, not the identity yet. But if I do thrice, okay, then I get 3, which is 0 bar mod 3, which is the identity in the additive group. Sorry? 6. What do you mean? What do you mean? Yeah? What's your problem? Sorry? What you said? Smallest, yeah, smallest, yeah, smallest, yeah, smallest. Of course, if you go to 0 3 times, you also go to 0 the 6th time, right? Because you already go to 0 at the 3rd time. Make sense or not? But this idea is very important, and later we'll carry forward this idea. Yeah. So that's why we add the smallest here. Okay, we add the smallest here. Okay, because you can see that, you can observe that if I do it in double, for example, I do it in a multiple of 3. If you do it in the multiple of your order, you still get to 0. Okay, but we won't say the order is 6. Order of 2 is 6 because we want to take the smallest one. Okay, smallest. So smallest here very important. You cannot say, oh, I checked already. X to the power 6 is 1. Then I put 6. No. You need to make sure that 1, 2, 3, 4, 5, you won't get back to identity. So that the 6 is the smallest one, for example. Okay. So I already checked that the order, the n equals to 1 and 2, they won't get back to identity. Okay. So 3 is the least smallest number such that s to the power n go to. Okay, so this is the subgroup, so cyclic subgroup, and then we have an order. Yeah, I haven't talked about this. So yeah, how about cyclic? So another very important property I left for you to prove at home. So another very clear definition of this cyclic example, is if you have order n, okay, the seemingly infinite set H, okay, will reduce to, okay, if the S has order n. Actually, you also have seen this phenomenon before. When does the first time you see an infinite set become a finite set? Okay. Yes, the integer modular arithmetic. You make the whole Z become some finite and set of n with n elements. Okay. So how do you do that? How do you do that? In Zn, who is the guy that has order n? In Zn, who is the guy that has order n? Always. Who at n times go back to 0? 1. Yeah, 1. 1. So the order of 1 is n, because 1 at n times you get n. N is modulo 0 in mod n. Correct or not? Okay, n times 1 is n mod n, which is 0 mod n. Okay, so 0 always has modulo n. So this question says that there's a subgroup generated by this. Okay, in fact, this is the whole group we have in Zn. 1, so 0 in this case, our identity, and then added 1, x is 1, and then 1 plus 1, 1 plus 1 plus 1, and then you should know that you get n minus 1. So this is our equivalent class. Okay, so please don't confuse with this one. So be careful. I still want to remind you about notation of element, because now we already have a lot of composition coming in. So sometimes it's convenient to write identity in some form. Okay, so the first notation I expose to you is E. Okay, sometimes we'll put identity 0 or 1. Okay, so what are the difference? Why we prefer one than the other? Okay, why we prefer one than the other? So if we put E, this is like, for example, the general. Okay, this is like for general abstract group. Okay, we don't care about how does it look like. We'll put E. Why we favor identity sometimes? Okay, sometimes we'll deal with function composition. Okay, function composition, like functions, we'll put identity because it's like an identity function. Okay, we have a short form of identity. The identity function. Why we favor 0 sometimes? Because 0 is the identity in the additive way. Okay, when the group is like adding together, okay, we will sometimes put 0. So for example, this Zn here is the 0 as an identity. And why sometimes we prefer 1? 1 is what? Is the identity for multiplicative. So let's say the group is multiplicative. Okay, we will put 1 typically. So for example, in this case here, why I put 1 here? Because I already assume, okay, seeing my law of composition as multiplication. Okay. Yeah, question? Yes. Yes. In fact, you see this in your textbook. If you do a tutorial question, sometimes they use 1 instead of E. Huh?
So in many GL and what is repeated as identity metrics, right?
Yeah. Yes, that's right. That's right. Hmm. Correct. Because you are writing one, so there's no difference. But in a books setting, matrix typically they will bold it. They will make it bold. Or if you want to make it bold by hand, right? Maybe you can draw something like this. Identity matrix. Okay. So you can see that different things will refer to same thing. Okay, same thing but incarnate in different way. Have a different incarnation. Okay, so the order of this. Okay, good. So very important. Have anyone tried to prove this at home already? Not yet. I posted out the proof already. You should at least read. Okay, and then try and generate the proof again yourself. Okay, after you read, generate again yourself without looking at it. If you start, read again, do yourself. Read again, do yourself. Okay. But if you really can't do, copy first. Okay, this is what I did last time. I think I did copy full proof copy until second year. So I also don't know what's the proof going on, but I copy the proof. It's like you writing essay. I'm not sure what's the experience of you writing essay. I think writing essay is a pain experience for me as well. So how do you first learn writing essay? Did you memorize essay or not? Some word. Okay, maybe you are better. Some of us just memorize the whole essay at the start. I mean, yeah, memorize essay. Because follow the topic, you memorize the essay. But of course, the exam won't come out with the same question. So, but that's one good thing about memorizing or copying. You get used to the logic, get used to the flow first. Okay, maybe you might not know what's going on, but slowly you will know. Okay, better than doing nothing. Okay. Yeah. Okay. So also we introduce a notion of cyclic group. Okay. So a group G is cyclic. Okay. If it can be generated by a single element. Okay, we call it a cyclic group. So everything can be recovered from one thing. Okay. Everything can be recovered from one thing. So for example, what kind of cyclic group you have seen already? Modular arithmetic again. Again. So what's the generator here? The generator. Yeah, I mean you can put everything in, but not that if it's cyclic, there's only a single generator. Okay, there's only a single generator here. One element can build everything. One is one. Okay. You can use one to build everything. Agree or not? So for example, in Z3, we have 1 plus 1, 1 plus 1, 1 plus 1 plus 1. Okay, which is 1, 2, 0. One can build everything. Okay, so this is a cyclic group. And then one important theorem, that's why we call it theorem, is every cyclic group is abelian. Okay, why is a abelian group good? the composition is commutative. Okay, later soon we will see there's a lot of things will reduce. The difficulty will be reduced because of commutative. Okay, so abelian is a good stuff. So you can see that in every group, okay, I left out the word group. So we can see that, what can we see? Okay, so what we see is here. So every cyclic group is abelian, but at first, what do we start with? So every group, we can find a cyclic subgroup. How to build a cyclic subgroup? The easy one. We just take an element in G and then composite forever. Okay. And then this group here, by the theorem, is abelian. You quickly see why is it abelian. What's the element in a cyclic group looks like? Some power, for example, n. Maybe two of them, n and m. Do they commute or not? Why they commute? Huh? Why they commute? Because the integer commute. Okay, because the integer commute. Okay. So it doesn't matter you do n time first and then you do n time, or you do n time first and then you do m time. Okay, they are the same in the end. Okay. So you can see that for every group, we can find an abelian group. So for example, Sn. Sn is not abelian, right? Last time I showed you. Remember? Like in X3, for example, 1, 2, 2, 3 is not equals to 2, 3, 1, 2. Okay? So Sn is not an abelian group, except S2. S2 is too easy already. So starting from 3 is getting harder and harder and harder. S3, S4, S5. So it's not an abelian group, but you can always find a cyclic subgroup. Okay, how to find a cyclic subgroup? Take one of the element and then compose with itself infinitely many times. Okay. So let's continue with today's jobs. So we continue with this cyclic group business. So next property is how about subgroup of cyclic group? How does it look like? How about if I take a subgroup of a cyclic group again? Okay, so I'm trying to find a subgroup again. How does it look like? Can it be any wild thing or not? Okay, so the theorem here says that a subgroup of a cyclic group is still cyclic. Okay, so if you go smaller again, it is still cyclic. So cyclic forever. Okay, until you reach the trivial subgroup. So how should we prove this? Okay, so let's say the subgroup H, let's suppose H is a subgroup of a cyclic group. So let's say H is the trivial subgroup. Okay, it's trivial subgroup. Is trivial subgroup cyclic or not? Cyclic, right? Because identity is identity, and then type keep forever. And then the inverse of identity is still an identity. Okay, so it is trivial. And then H is trivially cyclic. Okay, so let's say, so the hard case is let's say H is not the trivial subgroup. Okay. So what can we do? What can we do? So there's something inside this H. But remember, this H is coming from a cyclic subgroup. Okay, so you know how does the elements look like already. Okay, what you don't know is maybe what kind of integers is there. Okay. So we can pick the smallest positive integer m, okay, such that a to the power m is in H. Okay. You understand this construction? How does H look like? So the thing inside H should be a to the j such that j is in a subset of z. Shouldn't use the H again. Maybe I use maybe I. So it's an index set. Okay. We already know that our H, the element in H are a to the some power. Okay. But remember in the Z you have order, so you can pick the smallest guy. Make sense or not? Does it make sense? Does it make sense? Okay. Pick the smallest guy. Okay, so for example, H is equals to, let's say, A6, A4, A3, for example, then we pick the smallest guy, A3. Okay. Okay. So what are we proving here? We want to claim that C equals to AM generates H. Okay, which in other words, H equals to the group generated by AM. Okay? So this is our claim because we want to prove that it is cyclic. Let me tell you, proving question, when you see the statement and proof, it's not as hard as you come up with a statement and prove it. Okay, so if I already have a statement here, you should start with why is it true. Okay, you should take this line and then check whether it is true or not. So we take a subgroup. Okay, we want to prove that it is cyclic. Okay, so how to prove something is cyclic? If the group is generated by one element. Okay, so who is that element here? Okay, this is the guess you need to make. Who is the one that generates this subgroup? Okay. So my approach here is I pick the smallest positive integer such that AM is in H. This is my approach. I said that this guy will generate the subgroup. Okay. Is that okay? Yeah. Yeah. So let's see how we prove it. So what does it mean by this AM generate H? This means that every other element is a product of AM. Okay? It's a product of AM. Okay, let's see why is this true. So suppose D equals to, okay, suppose D is another element in H. Okay, suppose D is another element in H. We can write D equals to A to the power P, for example. for some p greater than m. Correct or not? Because I already picked the smallest guy out, all the rest should be larger than this guy. Make sense? Okay. So so what happened? Okay. So let's check whether we can split AP into AM or not. Okay. Let's split AP into AM. Okay. So how should we do? Let's see how many AM is in P. Okay, so let me see how to motivate this to you. So for example, you can take in your mind A2. Okay, here, for example, A7. Okay, so how many A2 in A7? So A7 equals to A2 times A2 times A2 times A. Right? And I already show you that it's abelian, right? So I don't care whether I A2A first or A2A, A2A, don't care. It's okay. Never mind. It's abelian. Okay. So what's this? A2 3 times, meaning A to the 3 times 2 times A equals to A to the 3 times 2 plus 1. What is this? Remember? What is this from discrete? What is this? Euclid algorithm use this. So this is the division algorithm. This is the primary school stuff. Division. 7 divided by 2. Okay. So let me recall to you the segment. So division algorithm. So this is the first thing you learn in division. 1 is the remainder. And so let me write it down. So if m is a positive integer and n is any integer. So you have a number, you want to divide it by m. Then there's this two number. Okay, there's this two number. Not just two number, they are unique. Okay, there's only one solution. So you need two numbers q and r such that n equals to mq plus r. Okay, and then there's a condition on r. Anyone know what's the condition on r? What's the condition on the remainder after you divide? The remainder have to be strictly less than m and then greater or equal to 0. Okay. So meaning what? So meaning we can split AP because P is greater than M. We can split AP division algorithm. We can split AP into multiple of AM. Okay, so let's say AMQ plus, sorry, not plus, because this is a plus R at the top, so it becomes MQ dot M. Okay. Okay, does everyone follow up to here? Okay. Follow can follow Okay. So what's going on here? We have AMQ AR, but we want to prove that it is cyclic, right? So if AR disappear, meaning all the P can be written as multiple of MAN. So we need to make this AR disappear. Should AR disappear? Huh? Should not. Why? Why not? contradict the choice of M. Okay. So if you suppose AR is in our set H, then just now you started with smallest one. You say you started with the smallest one. Okay. Then M is not the smallest anymore. Okay, so contradiction. So AR won't appear in H. Okay. So if AR is in H, this contradict the choice of picking the smallest integer M. Okay, so let me write it again. So if R is greater than 0, this contradicts the choice of picking the smallest integer M. Okay. Or in another word, what does it mean? For R greater than 0, AR cannot be in H. Okay. So there's only one possibility R can be. R can be 0. That's all. Okay. So the only way is the only way for the equation to hold is when R equals to 0. Okay. When R is greater than 0, then you contradict the assumption. Any question? Any question? No. Okay. So you can see that we somehow attach to numbers. Okay. The group operation reduce to number theory question. Okay. Okay. So the idea here is you have a group. Okay. You can take a cyclic subgroup. Okay. How to take a cyclic subgroup? Pick any element, composite. And then you pick a subgroup again. Subgroup of a cyclic subgroup is still cyclic. So you will forever cyclic until the trivial subgroup. Trivial subgroup is still cyclic. Okay. Yeah. So this says what? There's nothing interesting about the subgroup of cyclic group. So if you reach a cyclic group, maybe you can end already. There's nothing interesting there already. Okay. They are all cyclic, all the subgroup inside the cyclic subgroup. Okay. But this tells very important things in Z. Okay. Not just Zn is cyclic, Z is also cyclic. Is Z cyclic? Is Z cyclic or not? Why Z is cyclic? Who generates Z? Generates Z. One. Also one. 1 plus 1 is 2. 1 plus 1 plus 1 is 3. 1 plus 1 plus 1 is 4. Okay. Minus 1 exists. Why? Because axiom of group. And then you can go forever negative as well. This is the how you build natural number, right? Piano axiom. You start with 1. What's 2? Right? The successive of 1. So meaning 1 plus 1. What is 3? The successive of 2. 2 plus 1. This is 3. What is 2? 1 plus 1. So everything reduced to 1. 1 and then add 1. Add 1. Add 1. Add 1. Okay. Understand? Okay. Okay. Yeah. So yeah, last time I forget to introduce you a new word, corollary. You know what's a corollary? So corollary is a conjunction. So corollary is a conjunction. So corollary is a conjunction. Okay. 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 So coroll So you prove a theorem, and then some statement just follow easily from that theorem. We will call corollary. Okay, corollary. So now we prove a theorem. Now there's one statement easily follow from that theorem is the subgroup of Zn under addition. Okay, so maybe I don't write so many words. So Z plus precisely the groups nz, so addition. So the subgroup of Z is nz. So you can start with 2, and then you use 2 to build. So for example, let me give you an example. Otherwise, you will not imagine. So like this. So what is the group generated by 2? Any idea? What's the group generated by 2? 0, 2, yeah, even number, correct. Good. Yeah, even number. So I think you familiarize with 2z, right? Yeah, even number. Correct. Yes. Okay, so you can have 3z, so multiple of 3, 4z, 5z, and z. Okay, so this is a corollary. So one very important question, very interesting group. Okay, this is a very interesting group. So how about this subgroup here? One of them is positive. One of them can be 0. How about this group? M's R plus mx for n and m in Z. Does this look familiar to you or not? N plus mx, fixing R and x. Is this a group? Is this a group? Identity in there or not? How to build identity? How to build identity? What's the identity in this group? 0. How to build 0? N and m is 0. Okay. So is it close or not? Is it close? If you add 2 such number, does it still look like nr plus mx? Yes, right. Okay, n1 plus n2 times r plus m1 times n2 times r times x. Okay, so it is close. Can you follow what I say? So if you have n1 r plus m1 x, how do you add them together? Okay, I don't write it down. You try and compute. Does it still look like nr plus mx? What else you need to check? Identity check already. So this is a closure. And identity just now we checked where we just take nm equals to 0. How about inverse? Inverse exists or not? What's the inverse for everything? Minus n minus m. Okay, makes sense? So this is the number that when you add to nr plus mx is 0. Right? Left or right? Both. Both are, you need to check both. Okay, good. This is a subgroup. In particular, this is a subgroup of a cyclic group. Right? This is a subgroup in Z. So cyclic group, what's the property? Subgroup of a cyclic group is cyclic. In particular, this group is generated by one element. Who is that element? Can you guess who is this element? Generate this set. nr plus mx. Euclidean algorithm. Who generate this subgroup? R and S. but I only need one. So who? This is a cyclic group generated by one element only. Now, sorry? Yes, GCD of R and X. So this group is generated by the GCD of R and X. What's the GCD? What's GCD? Greatest common divisor of R and X. Okay. Greatest common divisor of R and X. How to find common divisor of R and X? What do you do? So let's recall for you, okay? Let's say how to find GCD of 6 and 2. Okay. So you divide, right? Okay, maybe 6 and 2 very fast. So let's do 7 and 3. 7 and 3 got nothing. 8 and no, don't want 8. Let me think. 8 and 8 and 8 and 6 3 Is it better? I think very fast, is it? Is it okay? What GCD got longer calculation? I'm thinking of one now. Okay, so what's the GCD of 18 and 3? I want to perform the Euclidean algorithm. A standard Euclidean algorithm. Okay, so what's the GCD of 18 and 3? It's 3. Bit stupid like this. Okay, never mind. So let's recall what's the definition of GCD of Rx is the first common divisor of Rx. Okay, so since this is the greatest common divisor of R and X, right? Okay, so in particular, NR plus MX is what? Is divisible by GCD of R and X. Okay, so there's this sum K. Does it make sense? Because it's the greatest common divisor. So the GCD divide R and X. Does it follow? Follow or not? Okay. So let me write some more things. So in particular, so for example, R is equal to K1 times GCD of R and X, and then X is equal to K2 times GCD of R and X. Okay. So in general, NR plus MX can be written as N times K1 GCD of R and X plus M times K2 of GCD of R and X. Okay. So you can write all the term as a multiple of GCD of R and X. Okay. So GCD of R and X generate the subgroup NR plus MX. Okay. Is it okay? Okay. Any question? Any question? Question? Okay. So yeah. So a new way to understand this GCD is you can build any number, any linear combination of R and X. Okay. You can use GCD alone to build them. Okay. Okay. So Jen got question? No. Okay. Okay, so these are cyclic group. So we will have a next definition. So how about our group is generated by more elements? Okay, what do we mean by that? So let's say G is a group, okay, and then we take a few more, okay, a few more elements, not just one, a few more. Then the smallest subgroup of G containing these elements, okay, is the subgroup generated by this element. Okay. So why I say smallest here? Okay, why do I say smallest? Because when we talk about generating group, we just says we just says we just need to satisfy the what property? Identity exists, inverse exists, okay, and then closure. So if you done this three axiom, then it is the smallest one. Okay. Because hey, in theory we can add more things into it. Okay, but we don't need. Okay. So as long as you satisfy the basic three properties, this will form the basic, the smaller subgroup. Okay. So if let's say if this subgroup you form is the whole is the O of G, okay, then this set will generate G. Okay. So just now we use one element to generate the group, but now we use more than one element to generate a group. Okay, and these xi are called the generators because you generate the group, so you are the generator. So if this set is finite, okay, if this set is finite, then your group is finitely generated. Maybe we look at some example so they will click into your mind. Okay, then G is finitely generated. In this case, we were right. In this case, we did not. G equals to the bracket of, sorry, I changed my notation, xi. Okay. Okay. So for example, what have we seen? Finitely generated. So Z is finitely generated by 1. Okay, cyclic group. 2. Zn is finitely generated by 1 as well. Okay. Or if you want to be pedantic, you put 1 bar. But in calculation, typically we ignore the bar because too many bar to write. What else? What else? Sn is also finitely generated. Okay. The most brute force way is to use all the n factorial permutation. But in general, it can be reduced. Okay. Maybe we will see it when we learn generators and relation later. Okay. So you can use the n factorial permutation to build it. So in a finite group case, you can use all the elements to generate it. Okay. But can you reduce the number of generators? Is the question. Okay. What's the least generator you need to use to build your group? What else? So, for example, R. Can R be finitely generated? Can R be finitely generated? R is an infinite set or finite set? R. Infinite set, right? But Z is also an infinite set, but it's finitely generated. How about R? No. Okay. R is a infinitely generated. It's not finitely generated. Okay. Okay. Yeah. Any other group you want to see? Want to check? Any group you want to check? So bear in mind, when we talk about group, they are what do I mean? They are composition of it. So for example, in Z, we are really thinking of addition. Z bar addition. Sn composition. R, no matter it's for addition or multiplication, they are not finitely generated. Okay. But remember, when we put multiplication on R, it's not R anymore. It's R throw away 0 because 0 is not equal to. Okay. So there's some subtlety you need to take care sometimes. Okay. Any question? Question? No. No. Yeah. About function composition. Depend on what function you want to look at. Which function you want to look at? Because function in general is not a group, right? So last time we stopped at the homeomorphic function, homeomorphism, which is what? Okay, no need. Okay, yeah. So that one is for continuous and bijective, but as long as you have bijective, you form the group already. Okay. Why I talk about continuous function because they will be useful in analytic in the analysis part. So is bijective function finite or not? So this really depends on what kind of function you have. So your function really depend on your domain. Really depend on the domain. Okay. Your domain is infinite or your domain is finite. If your domain is finite, then this is just reducing to Sn bijective function on a finite set. This is precisely commutation. This is Sn. So if f is infinite and then need to be bijective, I don't think it is finite. But we need to see the infinite set first. Yeah, depend on the where you define your function on. Okay. A function on the finite set, bijective, then you have the permutation. This is the Sn. Okay, so let me write down what is Sn again. So Sn is a function, not just function, it's a bijective function on finite set. Okay. And then there are n factorial of them. But actually we can reduce the generator inside. But together with the help of a relation. Maybe we'll touch on it later. Okay. Question? Got question? Countable, uncountable, infinite set. Yeah. So this is a bit like basis. Actually, someone confused with basis and generator. Someone asked me who is the guy. Who messaged me? Who asked me about basis and generator? Who I forgot already. But so this is similar to the idea of vector space. Like a vector space is infinite set, but you have a basis if you have control on basis, you know how the linear transformation map, and you know everything, every element inside your vector space. Okay, you can express every vector in terms of the basic element. This is also the same case. You have a group, you have a Z, for example, it's infinite set, but somehow you can get every element from this generator. Okay. But in vector space, you have two properties to play with. One is scalar multiplication, one is vector addition, okay, which is law of composition in this case. But here, we only have law of composition. We don't have scalar multiplication. Okay. So group is a little bit more restrictive. Basis have two elements. Basis have not two elements, two operations. Okay. Later we will reach vector space, which we will call ring general. Okay. Okay. These are mostly notation, and then you need to know if people write like that, what does it mean? And I think SN is still a bit vague for you, a little bit vague, is it? So maybe put S3. So S3, what is S3? S3 is the identity 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. Okay. If you have read Artin, right? Artin actually reduced this set to 2 generators, okay, but with some relation. Okay, yeah. Actually, you can generate this group with less. If I'm not wrong, you can generate this group with 1, 2, and 1, 2, 3. You can try. You can try. I think 1, 2 cycle and 1, 3 cycle can generate this group. You can try. Okay. 1, 2 cycle and 1, 3 cycle will generate this group. Okay. But to be precise, right? But to be precise, this is not the right group. You need to add some relation, which we will touch later. Plus some relation. Plus some relation. Okay. But yeah. So meaning you need to remember some relation inside Seng to show that they are true. This is true. But anyway, we won't go into that yet. Later we'll go into it. Okay, let's take a break until 9:20, and then we'll come back for homomorphism.哎，不一样，这个是1，这是1去3，1去2去1，这个呢？1去3，所以这个两个是不一样的。
这10个本来就是一个方程来的。
对，没错。对，来 ，bijective function on finite set。Tadi哪里呀？
赢了。
你要记住这个 notation，我们会放像我刚才讲，就是我的 identity 啊，有时候会写成 identity，有时候会写成 identity，通常是
一样的
为准，
对，
对，就是都是一样 in the sense that 它会符合这个条件，就是他加了别人或者别人加他。
像我那个一是代表
这个一哈，这个一的意思就是说，你看这个一啊，哦，我知道了，你说 in function form 它是什么哈？OK，in function form 是这个，in function form 它是这个1去1，2去2，跟3去3，因为它才没有做到东西嘛，identity function。
它不能表达像这样的整个
你真的要硬写的话，我上次有讲过，你要写这样哦，但是我们通常不会这样写。比如说，我们通常不会挤一个3在里面，我也不会挤一个2的，因为我们知道，如果我没有写的话，它就是不会动，被 fix 住了。如果你要想的话，只有它 compose 所有人的时候，还是对不对？因为你没有动到，你没有改变嘛，你没有改变它。
notation S3，我要讲你有想这个 S3。
这个 definition projective functions on a finite set with cardinality function
什么是 with
cardinality n， 所以你看它是一个 function on， 所以 S3 你看你把号码放进来 projective function on finite set with cardinality 3， 所以你是 function on 3 elements
就是只有1、2、3嘛？
对，可以加1、2、3，可以加3。
也可以加4、5、6，
可以，没有问题。
只要有3个数字有
Yes， 所以这个 group 如果你把它换去4、5、6是跟这个一样，所以1啊，什么4、5、6哈，4、5啊，然后6啊，然后4、6啊。
最重要的不是这些数这些字呢，
你可以这样讲，你可以这样讲，没错，可以这样讲，没有错。数字只是一个来，我们你一定要叫它一个名字嘛，对不对？最容易叫的就是号码哦，对不对？我如果再叫苹果、香蕉那些，不是很长吗？
讲从这个来啊，
哪一个？哦，怎样从这个来到这个哈？我没有讲怎样来，我只是告诉你，你 try 一下用这2个乘一乘，看一下会不会调出其他东西。
我们做过那三角形啊。
我做过那三角形，但是我没有把所有的 relation 告诉你，所以还不能够很准确告诉你。我只是这个你还不知道，现在你可以 try 的东西是，你 try 一下 compose 一下，会不会把其他东西弄？
就是这个 compose 这个，或者
或者自己 compose 自己。
有3种情况。
Yes，closure 吗？
像这边加，
就是说要加这些 relation， 我还没有告诉你，就我跟你讲会有这个东西以后。但是如果你真的还很兴趣的话，在阿听那边有，就是2点多 section， 它有写，就是阿听那本书
课本，
课本，阿听那本书2.3、4、5，前面就是我在教的这个附近，它有这个example，它就如果你有兴趣，你可以先看，之后我们会进到 generators and relation。那天我给的那个 relation 也不够，还差一个，我不想解释那个先。
这样子，但是我要讲就是这个你去跟他compose 那个符号我要用什么？因为不是这样用的。
乘，通常我们用乘在这里，
用乘就
我不会写乘啊，就写 dot 啊，那个 compose 那个 dot。如果你如果要写成，如果你要写成 function composition 也是可以，但是通常呢，我们是写 dot 是3这样，或者我们就直接乘哦，就像号码乘在一起吧，就知道在乘的。
从后面做起。
我们从后面做起，从 right to left，对，我们 convention 是 right to left，
我这个是173或371，
然后啊
1672、2671、371，所以3最后去到2。
，OK，你说这个对，对，从哪一个开始？3开始，3会去到，
也是这样子写啊，3去到2，
对，没有错，你把它总合起来咯，
然后需要放挂号，
还没有结束啊，你要算完它，2去哪里？
就是
继续算，
1、2、3我
都要知道，你都要知道呢，都要知道啊
所以不管我 start 从1至3
，yes
都
都可以，
可以，只要我算到完。
你可以 try 都可以，对。比如说这个2去1，停，1去3
然后
就回来了，对。
就关了。
你看啊，如果你从2开始啊，我跟你讲，你的答案就是2、1、3吧，对吗？对。如果你从2开始算，就是2、1、3，而且这两个 cycle 是一样，就是我可以规定这个 cycle 转，所以它叫 cycle。
这个等会儿什么意思啊？
哪个
也推导，用这个东西讲
啊？
我说就是用这个，就用这两个，用这两个
啊
transformation 能导致前面的所有的 transformation。
啊，可以把其他的造出来，
它就是这个 generation。
它就是 generate，对。但是如果我要写等于的话，我还要再加一些 relation。对，因为如果那些 relation 不符合的话，它这些其他数字是不会调出来。
我如果不懂这个，我可以写完它。所以是像刚才那个 R 跟 S，我不懂句式，我没有看出来 GCD，我就写 R 跟 S。
你就写 R 跟 S，但是我的题目是说我要它 Cyclic，所以我要找一个东西 generate 它。R 不能 generate 它 ，S 也不能 generate 它。谁能 generate 它呢？GCD 哦。
OK，
因为他们两个都被 GCD 除，然后它是那个最小的。
为什么 generation 可以是个 element 呢？也可以是个 group？
什么叫 element 是一个 element？
就是它这个不应该 group。
generator 是 element 啊，是 group 啊，什么问题？
它这个的 generation。
啊，对，它是 group 啊。
对，它是 group，但是之前的时候definition 是一个这个 generation 应该是 element。
generator 是个 element，对，没有，我是说这个是 generator，我没有说这个是 generator。通常我们画成这个东西的时候，我们讲它是个 generator，就是它里面的东西。哇，要这样仔细哦。
对啊。
或者你要的话，你就说这个是一个 generating set 哦，也可以 generating set 啊 generating set。如果你要讲这整个东西，它就叫 generating set， 里面的东西是叫 generator。这样可以，这样可以。对啊，是，Okay, hello, testing. Okay, so let's start. Before we start, let's take the attendance. Okay, we have quickly Venus. Yeah. With the there. Where's with the? Not here. Where is he? Please. No. Take. Don't know. His friend choose not to. With严苛呀，德瑞呀，Steven 也至于所有尊生呀，孙林凯仁金波华英皮熊英奇而已田家业 OK 家业 very early today 我不离开袁家文硕一定玉为燕博
陈烨、林静、董洁、一周、OK， 丁宇、柳晴、曾腾、硕宁，OK， 武力啊，天首先，李明、Grace、陈烨、嘉文got here 了 ，OK， 明修、Michelle， Ryan、Ellie、雪梅，子源 one， 子源 two， 他已经说子源就是他 right， 懂没？子源 right。啊，出去是不是？好像有看到。Okay, continue. Okay, good. So we have so many groups to play with now. So we have group, symmetric group, cyclic group. Okay. So cyclic group produce a way for you. Cyclic subgroup produce a way for you to build new groups. Okay. Yeah, cyclic. So now we want to study map between groups. Okay, this is a very important concept. Similar to function. Okay, after you study a space, you want to map between spaces. Okay, you have to map between spaces. So let's say we have two groups. Okay, what's the homomorphism? Anyone know what the homomorphism means? What is homo? What is morphe? Morph. What is morph? Form. A form. Yeah, a form. Okay, a form. Homo. Same form. Okay, same form. They got the same form. Homo. Yeah, homo. Yes, that homo is coming from the same word. Is a homo is, I mean, which homo you are referring? Yeah, the homo is the same. Same homo is same. Okay, homo means same. Okay. Homomorphism. Okay. So homomorphisms map a same form to same form. So what form are you looking for? A group form. Okay, a group form. Group form. Okay. So you need to preserve group properties. So what kind of property you want to preserve? Especially the closure. Okay, the closure. So meaning you want to send phi AB to phi A times phi B. Okay. How you should think of this equation? You should think of this as a commutative diagram. Okay. So how should you think of this commutative diagram? So you have a G to G prime. So you start with G and G prime. Okay. And then you have G. And then you have a G prime. Okay. And then you want to combine G and G prime. Let me see. Am I doing stupid thing again? Wait, let me rephrase what I'm trying to do. So we have a phi, okay, sending AB to phi AB. Okay. Another thing you can do is you send A first. Okay. Okay. And then send B to phi B. Okay. So in theory, these three things doesn't need to be the same. Okay. They don't need to be the same. But we impose the property that phi AB have to equal to phi A times phi B. Okay, so this is the multiplicative property. Okay, multiplicative property. So you can split your map into multiplicative order. Hey, I think I'm a bit blurred today. Too early. So I haven't tell you what's the homomorphism yet.
So what's the homomorphism? It's a map from G to G prime. Okay, such that the following is true. There's a commutative diagram here. Can you think of one commutative diagram? So let me try a bit blur. Don't have the image in my mind now. So I have a AB to AB. Okay, I remember what's the diagram already. So what do you do? Okay, what do you do? So here is the element in G prime. Here is the element in G. Okay. So let me draw this map here. So what's this map? This map is a phi map. Okay. So there's another route to phi AB. Okay, there's another route to phi AB. So what's that route? Okay, let me slowly recover. Now I don't have the map in my mind. I locally constructed. So what is how to get phi A and phi B now? Okay. So what do? I take phi A, okay, and phi B. How do I go forward? I compose them. Okay, so here I put a multiplicative. Or let me denote this map with a different color, so it's easier to distinguish. So we get phi A dot phi B in this case. Okay, so how to complete this? Okay, I think you are the first time hearing this word, right? So I'm writing a commutative diagram or square. Okay, let me justify to you why is it commutative. Okay, let me justify to you why is it commutative. So I haven't finished this diagram yet. So in G, I can take two elements out, which is A and B. Okay, if I send across to G prime, what I do, I just apply phi to them. Okay, if I go downward, what I do, I just multiply them. Okay, so you have two routes here. One, you can go to the right and then go down. The other one, you can go down first and then go to the right. Okay. A priori, these two paths don't the same. But if they give you the same thing, we say that this diagram is commutative. Okay. So this is the idea of this homomorphism. You want to make this diagram. Okay. So what's the diagram? So this diagram is you start with G. Okay. You start with G. Take two elements and compose them first. The other route, you apply phi first, okay, and then compose, okay. Then there should be the same, okay? Commutative. So when you see this kind of map, right, this kind of property, try and think if there's a commutative diagram behind it. Okay? So this is important, but this one is more important. Okay, this one. This idea will follow you if you go further in the pure maths. This one very good. And this is good. Good stuff. Again, must remember this commutative diagram, how to use this. Okay, how to understand this equation using the commutative diagram. Okay, very important. So there are two layers here, right? Okay, we have a domain, codomain, and how the element maps. How the element maps. Everything held by this diagram. So if phi is the homomorphism, then phi satisfies this commutative diagram. Okay. Okay. Question or not? Know how to read the diagram? Please ask. I cannot dictate your mind. Okay, please ask. Stupid question also allowed. Yeah. Question? Stephen, got question? Now? Simple, okay. Okay. Okay, so let's look at some example, right? So what kind of homomorphism? Actually, you see them before already. Okay, you see them before already. For example, determinant. Okay, determinant from GRN R to R cross. Okay, R cross, right? Invertible matrix cannot have zero determinant. Okay, is this multiplicative or not? Determinant of AB equals to determinant of A times determinant of B. Okay, this is the thing you prove in the linear algebra. Okay, linear algebra. So second, you also can prove that the sine function is also multiplicative. Remember, sine of even permutation is 1. Okay, but we say that even permutation is always can be expressed as another even permutation. So it is multiplicative. You can use that fact to prove. Another thing is quite elementary, exponential map. Okay, exponential map from R plus to cross. Okay, what is this? Quite elementary of this one. Can guess? Can guess? E to the x plus y equals to ex times ey. Okay, so can you see the subtlety here? Why the plus become a dot on the other side? Why is the right hand side, left hand side is plus, right hand side is dot? Why? Huh? Based on? Okay, yeah, of course, index law. Okay, how about group? Yeah, it's homomorphism, sure. But the first group is under addition. R plus. Right? The right group is under multiplication. Okay, so you can see here, I didn't put any notation here. Okay, so I assume what? I assume the element should follow the law of composition inside your group. Okay, so if I really want to be pedantic, right? Pedantic. So maybe I put like this. One is star. Maybe one is another star. Okay, 5 star. 5 star. Okay. So the first one you will put A star B. The second one you will put VA 5 star B. Like this. Okay. Can see it? Okay. So be careful, be careful. Next time, if I don't write down the law of composition, you should ask yourself, where does this element live in? Okay. And then we ask that space what kind of law of composition. Okay. Yeah, because sometimes we won't put so many notation because too many things. You see, now it's okay, but in future will be more calculation coming in. Okay. So this is the subtlety you need to know. Next, what kind of map? So for example, if you take any element G, okay, and you have a map from Z plus to G, which is sending N to AN. Okay, this is also a homomorphism. Okay, this is similar to 3 actually. Okay, similar to 3. I think another one you're also very familiar with. So if you take modulus of a complex number, what do you get? You get some real number. Okay, this is also multiplicative. Right. Right. So C of so if you take the length of C plus IY, okay, maybe times P plus IQ, okay, is equal to the length of X plus IY times P plus IQ. Can you quickly verify this or not? How do you quickly verify this?
How do you quickly verify this? This is very important. You need to think of a complex number in certain way that's very convenient for you. What's a complex number? Complex number live in where? Complex time. Complex time is like R2. What's the convenient way to record R2? Calculus 2 learn what? Use what to describe R2? Of course, vector. What the coordinate? Polar coordinate. Okay, polar coordinate. So you can write these as a radius times some rotation. Okay, very long. Okay, then from here you should be easily check that. The length multiplied together. Okay, from here. Of course, you can multiply out, but there will be a lot of job. Okay, but anyway, you use this one, it's faster. Okay, very important. This part build out the complex analysis. Okay, another thing very important, not very important, very interesting. Okay, very interesting. Very interesting on this one. Okay, remember what's U again? U is the union of root of n of unity. Okay, so what is root of unity? Still remember? Of e to the power 2 pi I times x. Yeah, okay, some fraction, depend on what n you have. Okay, and then what's this map? I send x to e to the 2 pi I x. Okay, so what's this? What is this? This is something you see in calculus 2. This is something you see in calculus 2, but not described in this way. Okay, what is e to the 2 pi I x? What's the length of this? Length of 2 pi I x is just 1. Okay, so this is precisely the unit circle. Okay, I sent a real line to the unit circle. Still remember this picture now? I sent a real line and then I wrap around the circle. Okay. So in calculus 2, you just learn the mapping of elements. But now this mapping respect composition. It respects composition. So if you add at the R first, is the same as you multiply at the y, at the u, sorry, at the u. Okay. Okay. So for example, p of x plus y equals to e to the 2 pi y equals to e to the 2 pi I x times e to the 2 pi I y equal to p x times p y. Okay, respect the group structure of both sides. Okay, respect the group structure. Okay. So this one is very important. This is a topology example. Okay. So you have a line you wrap around a circle infinitely. This is what we call a covering space. So this is what we call a covering space map. You use a line to cover a circle. Question? Yeah. I mean, Rx, you mean something like this? Rx. Mm-hmm. Mm-hmm. Not R anymore. This unit circle. I think no. Where we everything. Some form. Maybe you want to change R to something else. Huh? Polynomial. So you want to map polynomial into a point. What we do is map point by point. Yeah. Here what we do is point by point. This x is not a polynomial. X is a number. If you talk about okay. Okay. Yeah. Yeah. Any question regarding this map example? If you like, you should verify all these examples. Okay, satisfy the homomorphism. Okay, if no example question, we continue. So actually, this homomorphism map, right, is kind of restrictive. Okay, it's kind of restrictive. Although we only put one condition on it, which can respect the group structure. Actually, it's quite restrictive. Okay, what do I mean by quite restrictive? So immediately from this definition, we will have three properties. Okay. Okay. Sometimes homomorphism, people will call it morphism. Okay, morphism and homomorphism is the same. Okay, sometimes people call it morphism. Morphism. So let's say you have more than two elements to multiply together. Okay, you have more than two elements to multiply together. Okay, what is phi applied to the product of all these? Okay, what's the phi applied to the product of all these? Okay, and then we also can ask, where does the phi maps identity to? Okay. To where? Okay. And then phi maps inverse to where? Why are we interested in this question? These questions are precisely the axiom of the definition of group. Okay, axiom of a group. Okay. Identity. Okay, where identity go? And then where inverse go? Okay. Where the closure go? Okay. So phi x1 x up to xn is what? Is the split of phi of x1 multiplied until phi of xn. Okay. Where should the identity go? Identity should go to the identity. Okay, but in different group. So the first identity is in G, the second identity is in G prime. Okay. Where does the inverse go? Okay. So inverse, so phi of x inverse should go to bx inverse. Okay. So we're gonna prove this. So let's prove it. So A, how are we going to extend the idea of 2 to n? What's the 2 you need? You know how to multiply 2 elements. How to multiply n elements? Which means you use induction already. Okay, you are using induction. Okay, so you know how to multiply 2. Okay, how to multiply 3. Okay, so to say multiplying 3 things together, you need to tell me you want to group the first 2 first or the last 2 first. Okay, but it doesn't matter because associative in group. Okay, we just start with either one of them. So if I do like this, you can see that it is the product of 2 things again. So you can repeatedly apply phi. Okay, you can repeat. So in general, you need to apply induction. Does everyone know what I mean by apply induction? Induction on N. Does everyone know? Should I repeat the argument or you? Okay. 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 So apply induction is generally described, for example, this case in general. Okay. How you reduce n plus 1 case to n. N plus 1 is just 1 times n things. Okay. And then you can split it using the multiplicative property. And then the rest leftover n product of n element can be solved by inductive hypothesis, which means you repeat again. Is everyone happy with the proof of n? If you want to see the whole proof, right, I think it's in 2 point something. 2 point. Anyone know? 2 point. Yeah, around here. About Artin find the homomorphism part. 2 point. Okay. How about B? How about B? Identity. Okay, identity. How to prove? You must send identity to identity. Okay, how to prove it? So this is the trick. Okay. So what's the trick? You have limited resources here. Okay. So what to do? Identity can create identity. Okay. So identity equals to identity times identity. Okay. From here, it is product. So you can, because phi is a homomorphism, meaning this can be split into what? Venus. Yeah. What are the two of them? Phi identity times phi identity. Okay, good. Oh, good. Very good. So, do we know where phi of identity go? We don't know. We don't know yet. But what we know, phi of identity must be an element in G prime. Okay. To be an element in G prime, what do you have? There's this there's this one. But we know phi of 1G is in G prime. It's a group. Okay. So if it is a group, you can apply lessing of a group. Okay. In particular, which one is useful? A. So many identity. What thing you can apply? Cancellation law. Cancellation law. Inverse. Okay. Inverse. So we can apply inverse on both sides. We don't know what is it, but there must exist an inverse because phi 1G is in G prime. Okay. Then this implies that identity of G prime must be equal to phi 1G. Okay. So whenever you define a homomorphism, if this is not satisfied, then there's no homomorphism anymore. Okay. This has to be satisfied. Okay. If it is a homomorphism. Last one, C. How to prove mapping inverse to inverse? How to start? So that's the reason. There's a reason why they put B in front of C. Because we need to use B. Okay. B have to come first, then we can prove C. Okay. How to use B? Yeah.
phi of the inverse. Okay, sure. We start with phi of the inverse because question left. Okay, so let me write down what we want to prove so everyone are on the same page. So we want to prove A inverse equals to phi A. Okay, so Wayne says start with phi A inverse. Okay, so what can we do? What can we do? Oh, sorry, phi of identity. Okay. Sorry, I phi of identity. Okay, sure. We change our mind now. Okay, so let's start with phi of identity. Okay, and then so this is what? This is by part B. This is the identity of G prime. This is by part B. Okay, then what is S? Oh, okay. You mean compose? Okay, let's I didn't write the composition, so let's just put the multiplicative notation like this. Okay. Okay, so I split it up because this is a homomorphism. And then what does this mean? So phi A inverse is the thing that left multiply to phi A, you get identity. So this is the left inverse. So to find inverse, you need the right inverse as well. So you need to do another calculation. This is really similar to your common problem. So you need to do another side, which is A inverse A. Okay. So you also can use homomorphism to split it. Okay. This means what? Phi A inverse, right multiply phi A, you get identity. Also right multiply phi A, you get identity. So it's the right and left inverse. So they are equal. So inverse exists, and the inverse is phi A inverse. So yeah, is invertible. In particular, what's the inverse? Where the inverse of phi n is phi n. So the upshot is the inverse come out. Inverse come out from the morphism. How to prove? You need to go back to your inverse property. Okay, inverse property. Need to check these two properties. Okay, part 1 and part 2. Okay. Yeah. Any question before we finish for the week? No? Okay. I will see you next week.